In this video, we're going to look at the application to proportions of the central limit theorem, sampling distributions, and the law of large numbers. So when we talk about proportions, we're talking about a fraction, a ratio, a percentage that indicate the part of the sample or the population have a particular trait of interest. So when we talk about our nominal data, we're talking about categories, and so we would summarize that information as a percentage. For example, we might have a question that asks whether you voted Republican or Democrat in the last election. We would summarize our sample with a proportion that said, 55% were Republican. And then we want to extrapolate and say, well, what does that say about the amount of Republicans in the greater population? We could look at whether people identify as male or female. So we'd ask in terms of what they identify as, male or female, in the sample. We want to extrapolate to what does that mean for the demographics of the greater population. Maybe we're asking about whether they watch The Office. The answer is yes or no. We would summarize that with the percentage that watch The Office. So proportions can be a sample statistic and a population parameter. And we talked in our previous videos that if we are looking at the proportion in the population, then we use a lowercase p. And if we're talking about the proportions in the sample, we use p with a little hat on top. And a sample proportion is simply the number who fall into a category divided by the total number of people or items in the sample. So it's a percentage. So you're adding up those who essentially have a 1 if they have that characteristic of interest. They have a 0 otherwise. We add up all the people who are, or the entities who fall into that category, and we divide that by the total sample size. So we're getting a percentage who fall into a particular characteristic or category. Now, as with the means, if we were to collect multiple samples from a population, we could then try to estimate some proportion within the population. Now, just like we were talking about before with the average, each time we take a sample, so let's say we take a group of people and we find out what percentage are watching The Office, 10% in the first sample. We take another group, we ask them what percentage of them are watching The Office, it's 5% in that sample. So proportions will vary from sample to sample, and so they also have a sampling distribution, which means that the sample proportions can be treated as a random variable with a probability distribution. Now, we can use that normal approximation that we get from the central limit theorem, where we are able to take our samples and our proportions from each of those samples and apply it to the greater population. So if we have a sufficiently large sample size, the sampling distribution for a sample proportion will have an approximately normal distribution. A normal distribution, of course, means it has a mean and a standard deviation. Now, if we think back to our discussions about binomial distributions, when we talked about the binomial distribution, the mean was n times p, and the standard deviation was the square root of n times p times, we called it q at the time, which is just 1 minus p. So it was the number in the sample times the probability of success times the probability of failure. Okay, so we've seen this before with the binomial distribution. Well, our sampling distribution for our sample proportions is going to approximate a normal distribution with that mean of n times p and a standard deviation of n times p times 1 minus p, which means we can take that typical z-score that we've seen before, and you'll recall our z-scores, right, were originally x minus mu divided by sigma. So we can take this and put it in here, and we can take this and put it in here and do our standardization. Now, and that's what you see right here, x minus np divided by the square root of np times 1 minus np. Now, this, though, is not a sampling distribution standardization because this is X. But our sampling distribution and our approximation of a normally sampling distribution says that we could take that and we could divide by n, and then that is essentially X bar. So then we're looking more like the sampling distribution for the means. So what does all this mean? Well, this formula here, which is originally X minus mu divided by sigma, using the mean and standard deviation we know from the binomial distribution, gives us that formula. If we divide by n, we're starting to look like the sampling distribution for the mean. We've seen that before. And if we are then going to reduce that down, get rid of the n's, we actually end up with this formula. So you don't have to do any of this math. I'll just wave my hands. You can trust me here. The z-score for proportions, what you need to know is that the z-score for proportions is p hat minus p. That gives us our sampling error, how far away the sample statistic is from the population proportion. And then the bottom of that formula is p times 1 minus p divided by n. That is going to be your standard error. Notice that you're dividing by that n. There's that adjustment there for the sample size. And we are looking at our variability in terms of the probability of success, 1 minus the probability of success. So we can standardize our probability and then use our z-score to do the same thing, to extrapolate from our sample to the greater population. So we can use this normal approximation when we have a random sample. So we're back to probability distributions, not the non-probability distributions. So we need to be talking about, this is the slides you've seen before, we're talking about probability samples, not non-probability samples. So if we have a random sample, then we have a probability sample. It reflects the population. Non-probability samples, we don't know what level they reflect the population. So if you have systematic stratified cluster or simple random sampling, then you have a random sample. So we can do some inference about the population. We are assuming here that observations or trials are independent. If we're going to be able to use this binomial distribution characteristics, then we need the observations or trials to be independent. So when we look back at the examples of a voter, are they Republican or Democrat? Two categories, Republican or Democrat. And the likelihood that I'm a Republican is the chances of grabbing someone who's a Republican, they aren't dependent on each other. So if you pull one Republican to be in your sample, it doesn't mean the next person has more or less likely chance to be Republican or Democrat. So it's like the coin toss. We toss the coin. Each time you toss the coin, whether you got heads or tails, that probability of 50% held true. What you did the first time didn't change what happened to the second time. So when we're looking at, is someone identifying as male or female, if we are having just these two categories here, and the likelihood of someone being male or female doesn't impact the likelihood of the next person being male or female. So we're assuming they are independent of each other. The outcomes don't affect each other. The probability of whatever we're looking for, whatever we've labeled as the success, that's the characteristic of interest, that probability doesn't change as you pull certain people into your sample. The size of the sample or the number of trials must be sufficiently large. So we talked about for like the average, the general rule of thumb was a sample size minimum 30. For proportions, the rule of thumb is that your n times your probability must be greater than 10, and n times 1 minus your probability must be greater than 10. So at the bare minimum, your sample size n must be big enough that when multiplied times the probability in the sample, you get more than 10. So, for example, if I had a sample size of 5 and there's a 50% chance of probability that people are Democrats, that is 2.5. That's not a big enough sample. Okay, so we need a sample that's big enough to get us to be more than 10. So if instead I made this a sample size of 20, when the probability that someone is a Democrat is 50%, then you can see that's, well, it's not quite enough because we're exactly at 10. We should get one more, the sample size of 21 to get that. Then we look at the other one. What's the probability of failure? So you want to make sure they're both more than 10 at a minimum. Of course, when we talked about previously about sample size, and of course I scrolled through to the different one, you'll recall the conversation we had here in terms of calculating sample size, so that n times p greater than 10 and n times 1 minus p being greater than 10 is a bare minimum, but this measurement is better for determining your sample size for your proportions. And go back to that video where we did that calculation to figure that out. But at a bare minimum, bare minimum, n times p greater than 10, n times 1 minus p greater than 10. Okay. Now, when it comes to applying the central limit theorem to proportions, if our sample size is relatively large, then we can approximate the normal distribution. That means that the average proportion of so each time we take a sample, we say, okay, what percentage are Republicans? First sample we take, it's 20%. Next one we take, it's 60%. Next one we take, it's 70%. The average of those proportions is the population parameter P, is the proportions for the population. So the average of the proportions is the population proportion. When it comes to the standard error is the standard deviation of the sampling distribution. So how much variability is in the sampling distribution? That's going to be p times 1 minus p over n. So essentially what we're going to do is we're going to take samples and get a bunch of p's. And sometimes those p's will be, let's say, 50%. Sometimes, let's see, 60%. If we're looking at percentage of Republicans, for example. Okay. The average of that sampling distribution will be the population parameter. The variability of that sampling distribution, the standard deviation of that sampling distribution, is going to be the square root of p times 1 minus p over n square root, which means that we can use our central limit theorem that says if we do not know what the population proportion p is, we can use the estimated standard error to estimate the standard deviation of the sampling distribution, and we'll later then create some confidence intervals that we'll use as part of that. So notice that this here contains p, not p hat. And so if we don't know what p is, because the whole point of doing this is try to estimate what's happening with the population, we'll actually estimate it with the p hats instead. Okay? So let's show how we would use all this information. So it's been hypothesized that less than 10% of 3-year-olds already know how to write their first name. Out of 85 randomly sampled 3-year-olds, 11 are able to write their name. So we need to first figure out in our sample, what is p hat? So what is the proportion in the sample? Well, if 11 can write their name out of 85, then our sample statistic is 11 divided by 85. And what do we get? And it looks like sometimes I pre-calculate these and write them down and save us time, and others I don't, so then I have to do it here. 11 divided by 85. All right, 12.9%. So what is the mean of the sampling distribution of p hat, the expected value of p hat? Well, in this question, it's been hypothesized that less than 10% of 3-year-olds already know how to write their first name. So we are looking at a p, so we think p is 10%. And what we're looking at is that probability of that sample being in agreement or disagreement with that hypothesized population parameter. So the mean of the sampling distribution of p hat, the expected value of p hat, we think the population proportion is 10%. What is the standard error of p hat? Well, standard error is equal to, and we know this, we have this formula here, and it is the square root of p times 1 minus p over n. Now, when we are looking at the fact that we think that p is a certain value, we'll use that. And then when we're doing, say, our confidence intervals and we don't have p, we will use p hat within that calculation. But here we can use p times 1 minus p over n because we are actually looking at it. We think that this is the population parameter. So what we're doing is we're going to then take 0.1, try to put it somewhere that my head is not shown, 1 minus 0.1 divided by n here being 85 and taking the square root of the whole thing. So if we're doing that calculation here, that is 0.1 and 1 minus 0.1, which is 0.9. So we're doing equals this times that, okay? And we are then going to take that and divide by 85 and then take the square root of that. Okay, so right now we are looking at a standard error of 0.03. All right, so if we were looking at the approximate shape of the sampling distribution of p hat, we would have that normal distribution where the mean was the 10% and the standard error was the standard deviation of that distribution. So let's look at the last question. What's the probability of getting a value of p hat greater than the one we observed in our sample of 85 randomly selected 3-year-olds? So we want to know the probability that p hat is greater than the, what do we get? 12.9% that we observed in our sample. So to do this calculation, what we're going to do is we need that z-score. Might crap out on me here. And our z-score is going to be p hat minus p. So if we go back here, p hat minus p, so this is the sampling error divided by the standard error is how we get our z-score. So we are going to do p hat minus p, and p hat was 12.9% minus 10%, so we get that 2.9%, so that's 0.029. And then we're going to divide that by the standard error. Our standard error is that 0.03 we just calculated. Okay, so just get us our exact number here. All right, 0.129 minus 0.1. Put an equal sign in front of that. Make sure I did that right. 0.129 minus 0.1. So we're going to take that number, 0.029, and we're going to divide by our 0.0325, we get 0.89. So we would go to our standard normal table, we would look for 0.89, 0.8, and then the part you can't see that my head is covering up, 0.89, 81,327. So that gives us the probability that z is less than 0.89 is 0.81327. In this particular question, we want to know what's the probability of it being greater than that. So we want the other direction. So we will do 1 minus 0.81327. 1 minus 0.83217. And we get 16.8%. Okay. So here, when we did this with standard normal table, right, we found the z-score and we then looked up 0.89. If we're doing this in Excel, then we can use that same normal distribution that we used before, except for the problem is with this normal distribution is it's looking for an x value, a mean, and a standard deviation. So it's not really going to work for our proportions. You can instead use this norm S dist, and the norm S dist, you give it a z-score, which means you have to do that first part of that calculation separate from Excel, but you could type in 0.89 as your z-score and cumulative equals true. And you can see here it gives us the 81,32671. So if you're doing this norm S distribution, that's the standard normal distribution, you give it a z value, but that means you already have to have calculated z, which then means, if I go back to our slides here, that we had to do this part of the calculation separate, where we found our sampling error and our standard error before we put it into Excel.